Okay, good morning. Let's continue the natural language processing class. So for this week, we learn another type of discriminative models called log linear models. And then we try to unify the perceptron and support vector machine models that we learned with log linear models. So this chapter consists of four main parts. Okay. First, we look at a new type of model. And then we come back and discuss the training of support vector machines, which we didn't discuss last week. Third, we discuss the generalization of the linear models we learned. And finally, we talk a little bit about how to combine different sorts of models together. Okay, so first of all, before we introduce our new linear model, let's take a recap of the linear models we have learned. So from last week, right, we unified all these models into the same form. So where you can see the features that we extract can be represented by a long vector, right, phi. Phi is extracted from the input x and output class label c. Right, so we have a long feature vector. And the linear models all score the input-output pair x and c, right, according to this representation, phi, x, and c. We learned a generative model, naive Bayes model, and two discriminative models. And they score these feature vector differently. Like for naive Bayes, you assign probabilities to each feature. Right? The probabilities consist of two types: the class label log probability, log PC, and the word class pair probability, log PW given C. Right? So basically, you organize these two types of probabilities into parameter vectors for every class. And then when you're given a pair x and c, you extract the features, you multiply the feature with the parameter vector, you get the log probability, right, of each of this particular input-output pair. For naive Bayes model, all of these parameter probabilities are trained individually, right, using maximum likelihood estimation. You do relative frequency calculation, and you estimate each of the parameters. That's a generative model. When we come to SVM and perceptron, we also define a parameter vector which is of the same size as the feature vector, but then the parameter vector is trained as a whole, right? Trained as a whole. For SVM, to optimize a margin-based objective function, right? To make gold class labels score higher than incorrect class labels. For perceptron, we have an online learning algorithm, right, to that end. So this is great. We unify all the classification models that we learned into the same form. Now let's compare the advantages. So for SVM and perceptron, last week we learned, okay, they can accommodate more overlapping features or richer features as discriminative models, right? As a result, you can control the dimensionality of your feature vector space. So you can have a high dimensional space which allows your training instances to be linearly separated, right? But for the generative model, naive Bayes model, we don't have this control. We have to follow the generative story, right, to define all the features that we have, to define the conditional probabilities. We used Bayes rule, we used probability chain rule, and independence assumptions to derive this parameterization, right? So we derive the generative story, and we have to abide by the story. We cannot change the features. So what's the advantage of naive Bayes? Okay, so on the one hand, it is more structural, right? In the sense that we know how each input-output pair is generated, so it's more interpretable. In a sense, we have a structured generative story. On the other hand, we've got a probability. This is what SVMs and perceptrons don't have. So in those models, you get a score, right? So you are given a document, and the sports class is scored 125, right? The finance class is scored 22,000 or something. You don't know how to interpret these scores, and some of the scores can be negative as well. So you don't immediately know, like, the absolute value, what it means, right? But for naive Bayes, you know, given this input x, the probability of the class label C is 0.6, and you immediately know that the chance of having this class label is 0.6. So you know how to understand this score. Okay. So is there a way to combine the best of both worlds? So the goal is to build a discriminative model, right? Discriminative model that gives you a conditional probability score, so that you can both have rich features as you want, and a score that you can interpret. How do you do that? So in order to do that, we might think about how to turn the theta dot phi score, right? The score that perceptron and SVM had into a probability. How do you do that? Well, we can borrow the formality of naive Bayes. Let's look at naive Bayes again. So the conditional probability is calculated as the product of the conditional word probability given class and the class probability. And if you take the log of this conditional probability, PC given D, you get the sum of log P W given C and log PC. Right? So the latter on the right hand side of the equation is the linear model that we had in the table. Right? So there is something. The log of the probability is the linear model. So intuitively, the probability should have something proportional to the exponential form of the linear model, right? Or e to the power of theta dot phi, something like that. Okay, this is the inspiration we got from naive Bayes. But if you only have e to the power of theta dot phi, right, as a score, it's not a probability either. Right? It's still a real number. Well, it's a number above 0, but it's not scaled to be a probability. How do you solve the problem? Well, you can do some normalization. So let's look at normalization for multi-class classification and for binary classification respectively. So first, let's look at the multi-class case. So you have you want to calculate py given x, where the input is x, output is y. So to that end, you first extract the feature vector phi xy, okay, to map this input-output pair into the high-dimensional vector space, and then you try to score this one by using a model parameter theta. So this is the parameterization, right? Theta dot phi, you get a score, and you calculate e to the power of this score. Okay. Now for every class label y, you calculate e to the power of theta phi xy, and how do you normalize that into a number between 0 and 1? You just divide, okay, the current score e to the power of theta phi by the sum of all class labels y prime e to the power of theta phi. Okay. So actually, this function can be denoted as a function softmax. Softmax. So this softmax function does the normalization. So when you have a particular class label y belonging to a set of classes capital C, you calculate the probability of this class label by e to the power of theta phi xy divided by the sum of y prime belonging to C e to the power of theta dot phi y prime. Okay, so that normalizes the score to a number between 0 and 1. Why is that a probability? Because if you add the normalized score of every class label y prime together, you get 1. You get a total of 1, right? So it means that this is a probability. So, in other words, we did a simple trick. We applied a softmax function to the score theta dot phi xy, okay, to normalize this score into a number between 0 and 1, and we got a probability. How do you train the model so that the score is really a probability? We leave that to later, but at least we get a score 4, okay? Softmax theta dot phi is for multi-class classification. For binary classification now, well, we could also do a softmax activation, right? But here, let me introduce a more traditional normalization method. Okay, so it's still an activation function, but not softmax, but called sigmoid. Similar to softmax, so sigmoid is also an exponential activation function. So it's proportional to e to the power of x, sigmoid x. But it is a score that is calculated as the equation shows, right? E to the power x over 1 plus e to the power of x. So this is the sigmoid score, okay? So how do you do binary classification? Okay, so we assume that this x is a feature vector that represents the input document, okay? We learned last week by beginning with binary classification. So this phi x is a feature that represents the input document. And we want to score this input document as a positive class by defining a parameter vector theta, so that theta dot phi is a score that represents the positive class, right? And we used to say if theta dot phi is greater than 0, then we predict a positive class. Otherwise, we predict a negative class. This is what we did for SVM. When theta dot phi is above 0, the vector is above the hyperplane, right? Otherwise, it's below the hyperplane. So that's what we did. And now we want to normalize this theta dot phi x into a probability score. Well, we normalize it into a number between 0 and 1 by applying the sigmoid function, okay? This sigmoid of theta dot phi x will denote the probability of x being a positive document. So what's the probability of the negative document then? We just use 1 minus this score, okay? So 1 minus sigmoid theta dot phi x. That achieves the normalization. Okay. So this is for binary classification. And you can easily see that when theta dot phi is equal to 0, then sigmoid of theta dot phi is equal to 0.5. Exactly the halfway from 0 to 1. How do you prove that? Just look at the equation, the definition of the sigmoid function. Okay. So this model, I call it a log linear model, but if you take a machine learning class, maybe it's called a logistic regression model. Okay. It's a binary classification model. So for now, let's just name it binary log linear model for for binary classification. Okay. So we've got a form of log linear models for both binary classification and multi-class classification. The next thing we worry about is how do we train the model so that the number you get, okay, is really a probability. How do you ensure that you can train the model to really get a probability score? Okay. Here we still borrow the idea from week two. So how do you train a probabilistic model? You have a training objective function, right? To maximize the likelihood of your data, right? So you can apply the same principle. Suppose that you have a set of training examples, right? X and Y pairs, where X is a document, Y is a class label. You want to train your model to fit the data, right? So this is the same as SVM and perceptron. But now, in order to get a probability, right, you apply maximum likelihood estimation. The goal is to make the data that you see the most probable. All right. So how do you denote the data probability, the likelihood function? Well, you use your model so that your likelihood will be computed using your model parameters, so that you can optimize your model parameters through the maximization of this objective function. Now, let's define the objective function for the binary classification problem. For this problem, we saw that y is equal to positive 1 is given by the logistic function, the sigmoid of theta dot phi x, right? So this is y equal to positive 1. Now suppose that in your training data, you have a number of input documents with a positive 1 class, and you have a number of input documents with the negative 1 class. The whole data likelihood is the product of both type of classes, right? So for the convenience of notation, let's denote the positive class instances as x I plus, and the negative class instances as xi minus. Right? For the positive classes, the probability is sigmoid of e to the power of theta phi over 1 plus e to the power of theta phi. For the negative classes, the score is e to the power of positive class labels. We have the total likelihood as the product of I plus. Okay, so this I plus are all the indexes for the positive axis. So I say I plus. This is their probabilities, right? By the product of I minus minus this one is I minus. This one is now. So this is the training object for binary classification. We want to maximize this function. How do we do that? As we learned in chapter 2, okay, in order to maximize this function, we take the derivative of this function with respect to the model parameter. What is the model parameter? So let's take this derivative. But if we take the derivative with respect to this function, it's a little bit difficult. But if you turn that into the logarithm form, it turns out to be easier. So a log of e to the power of theta phi is equal to theta phi x. Okay. Here, log in the denominator is minus log of sum I plus 1 plus e to the power of theta phi xi plus. So this is the logarithm of this one. Let's see. No, we don't have to sum up here. Yeah, so this is the first half, right? So if I did it incorrectly, you can correct me. So this one, if we turn this into log, then it's sum of I minus, right? And this becomes 0, and this becomes log 1 plus e to the power of theta dot phi xi minus, right? This is the logarithm of this one, okay? So when we maximize the data likelihood, we maximize the logarithm form of the data likelihood. Or we maximize the log likelihood, okay? Log likelihood. Alright. So we maximize this function by taking the derivative with respect to theta, right? So we could do that together. Let's do that together. When we take the derivative with respect to theta, okay, sum of all positive data instances, this part becomes phi x, right? For this part, when we take the derivative, it becomes minus the log of something. Derivative chain rule is 1 over this thing, right? 1 plus e to the power of theta phi x. And then what's inside, right? We take the derivative with respect to theta, okay? So because there is an exponential function, so this is equal to e to the power of theta dot phi x, right? Now, which one do we take? So this is I plus, this is I plus, this is I plus. Now we take this part, right? The derivative of this part with respect to phi. What is it? Theta with respect to theta. So it's phi itself. Phi xi plus. This is the derivative of the first part. Let's continue. I minus. A logarithm function, use the derivative chain rule. What's inside? I put it in the denominator. Theta phi xi minus. And then this part. The derivative of this part, e to the power of theta phi xi minus, right? And now this part. This part take the derivative with respect to theta phi xi minus. Okay, we're done. We're done. So you remember week 2, right? When we try to optimize something, we take the derivative, and what we do? We set the derivative to 0, right? We want to set this thing to 0. When we set this to 0, we find a value of theta, okay? But you all see, this is a quite complicated function. If you set it to 0, you don't get a closed form solution. right? You don't get a closed form solution to this equation. So what can you do in order to optimize this function? Okay. So when we don't have a numerical solution, or when we don't have a closed form solution, we turn to numerical optimization methods. Okay. And here I introduce one that is used very frequently. It's called gradient descent. Gradient descent. Okay. You have an objective function. You have a goal to optimize, which is the log likelihood, and you know the derivative of that one with respect to your model parameter. You want to adjust your model parameter to maximize its value. Okay. But it doesn't have a closed form solution. So you use gradient descent. The basic idea, okay, is to randomly initialize your model parameters. Randomly initialize your theta. Now you immediately have a value of the objective function. Now, you want to maximize that function. You need to adjust your theta a little bit and a little bit, alright? In order to maximize that function. Without losing generality, maximizing log likelihood is equivalent to minimizing negative log likelihood, right? So if you minimize the negative log likelihood, you want to adjust your initial theta step by step so that your objective function is minimized, okay? It is like you're originally standing at a random location in a mountain slope, in a mountain ridge, okay? You want to climb down the mountain, okay, to the bottom, to a minimum point, or local minimum point. You cannot see where the lowest valley is, but of course you can observe according to the current ridge where the lowest point is, okay? Now the basic idea is you start from a random location, okay, random theta, and you climb down the mountain by changing your location a little bit, okay, and re-observing where you are, and then you change your location by making one step further, okay, until you get to the local minimum, your local value. That's the basic idea of gradient descent. But which direction do you go? You go the steepest direction downslope, okay? What is the steepest direction, okay? You have a delta theta, okay? An incremental step towards a direction that's the steepest. And it turns out that this direction is the derivative of your objective function. It's what we calculate here. That denotes the direction, okay? Now you have the algorithm. So basically you randomly initialize your theta and you calculate the derivative and you take a step down the slope in this direction. But how much? How large is my stride? How much is my step? Basically you apply a ratio, okay, to your gradient. The ratio is called, is named alpha, it's denoted as alpha. It's called the step size. It's a positive number, okay? You use alpha multiplied by your gradient to take one step, and you repeat that until you reach a local minimum value of your negative log likelihood, okay? That's the pseudocode. That's the pseudocode. But when you get this principle, you look at the gradient again. You look at the gradient again. So this gradient is a little bit complicated, right? Can we simplify this a little bit so that we can better understand it? So let's just look at this part, okay? Look at this part. For this part, at least, we could extract a common factor out, phi of xi plus, right? We could extract that out, and this one becomes 1, okay? That doesn't simplify the equation much, but if you observe it a little bit more, So this whole thing, what is it? Can someone tell me what it is? Yes, it's the probability of y equals to -1 given xi plus, right? This is the sigmoid function. This is the model score. Sigmoid of theta phi, right? So this is sigmoid of theta phi. So this is the probability of y being positive 1 given x. So 1 minus this thing is the probability of y equals -1 given x, right? This one is the probability of y equals 1 given xi minus, right? So this is the model probability. So in the end, we got a gradient, or we got a derivative that is proportional to the model probability of the negative class for positive instances, and proportional to the probability of the positive class for negative instances. Okay? And we do some parameter adjustments, multiplying alpha. Okay? We'll come back to that later. So this is something tangible. And this whole thing is simpler now. If you look at this thing, you calculate the model score of an instance, and your gradient is proportional to this model score multiplied to your feature. That's the algorithm. When you execute gradient descent over a large set of training data, you find a problem. The problem is that you have to worry about the sum. Here is the sum, right, of all data instances. Here is the sum of all negative instances. Well, you have to accumulate gradients over the whole data set, right? Before you take one step down the slope. That could be slow when your data set is huge. To address this problem, people design a faster alternative, not as accurate. Okay, so this is an approximation of gradient descent called stochastic gradient descent, or SGD. What does it do? Well, it doesn't go over the whole training set at each step, but it goes only over one training instance at every step. Okay, we still randomly initialize the model parameter vector, and then we try to plot down the slope in the steepest direction. But here, instead of making decision over the whole training set, we make decision after every training instance. Okay, if you have 10,000 training instances, I just look at the first instance, I calculate its derivative. Okay, and I take the step size alpha times this derivative, and I add this thing to your model parameter vector. Okay, so essentially, for a positive instance, for a positive data instance, we just add this one multiplied by the feature vector, okay, to your theta. Okay, does this sound familiar with something? Okay, we'll come back to this later, right? So let me recap. What does a stochastic gradient do, right? So when you train a binary log linear model, you randomly initialize your theta, okay, and you go over your training instances multiple times, right? For every positive training instance, you add a proportion of your feature vector to your model parameter vector, and you're done, right? You go to the next training instance. If it is a negative instance, you add that proportion of your feature vector to your parameter vector, and you're done. You move on to the next instance. You iterate through all the training instances until sort of your object, your function doesn't go down anymore, and you stop. Okay. This definitely looks familiar with something we learned last week. We'll come back to that later. Alright, so pseudocode is shown here. So this is the stochastic gradient descent algorithm, okay, for the binary log linear model. On the left hand side, you see the pseudocode. On the right hand side, you see the equations that I just gave you on the whiteboard. Right? They correspond to each other. Alright, so after we learned the binary case, let's move on to the multi-class case. You remember, for multi-class classification, we had a softmax function over theta dot phi instead of a logistic regression case. So, when you have a set of training data, you still can have a log likelihood function, right? So, to save time, I don't derive this on the whiteboard. But if you're interested, you derive it yourself according to what we have for the binary case. So it's as shown in the equation, the sum of all the training instances. So theta dot phi. This time, the phi is extracted over both input and output, as we discussed last week, right? How do you cut the vector space in one cut for multiple classes, right? You increase the dimensionality by integrating the output label into features. So you have phi x y, and its log likelihood is the sum of every instance theta dot phi x y minus the log of sum of all possible class labels c belong to capital C e to the power of theta phi x c. Okay, it's very similar to what we have here. The whole derivation process is very similar to what we have here. Now, for every training instance, okay, the log probability is shown as theta dot phi minus log sum e to the power of theta phi. This thing. And you want to take the derivative, okay? You want to take the derivative of this thing with respect to theta. Again, I don't show you the details, but I highly recommend that you do it yourself. Okay, you will familiarize yourself with the process, and you get something that's analogous to what we have on the whiteboard, which is shown in the last equation. The derivative of log y given x over theta is equal to the sum of all possible class labels. Okay, the feature vector of your gold class label minus the feature vector of your current class label multiplied by the probability of this class label. Okay, this is your local gradient. Okay, and if you plug this into your gradient descent pseudocode, you get this pseudocode. Okay, you randomly initialize your theta, and you use the current model to go through your training instances multiple times. For each training instance, you first calculate its model probability, okay? And then you do a parameter update, okay? By adding the gold feature vector to your parameter vector and subtracting the feature vector of every class label, okay? You take the difference of these two feature vectors multiplied by the current class label. Okay. This is your gradient. You multiply this gradient by step size. This alpha is also called learning rate. Learning rate. The step size is also called learning rate. So you multiply this gradient with the learning rate, and you update your model and you go to the next training instance. Iterate through all the training instances, multiply times, and you finish training. Okay. Finish training. Now we have a gradient descent method. Or we have a stochastic gradient descent method. The gradient descent method is slow, but it's accurate. The stochastic version is fast, but it is an approximation. Is there a compromise? So something in between, okay? So it's a faster than gradient descent, but more accurate than stochastic gradient descent. It's called a batch stochastic gradient descent, mini batch stochastic gradient descent. The basic idea is also very simple. So you accumulate, right, the gradient of multiple training instances as a batch. Okay, you cut the training examples into small batches. Okay, and for each batch, you accumulate the gradients together, and you make a model update before you move on to the next batch. Okay, so there's a concept called batch size. So how many training examples do you want to put into each batch? Let's make it capital M. Okay. No. So let's take the number of batches. Okay, as capital M, and then you can see that for gradient descent, so this number M is equal to 1. The whole data set is one batch. Okay, batch training. For stochastic gradient descent, this number is equal to n. N is the number of training instances. So every instance is a batch. But in general, the mini batch stochastic gradient descent has an n between 1 and n. And pseudocode is shown in the next slide. So rather than accumulating gradients over the whole data set, you cut the data set into m subsets. Okay, for each of the m subset, you accumulate the gradient and you do the model update. All right, so this is a batch training. So whether you apply batch and what kind of batch size you design depends on the data set. Okay, so in your lab section, if you want to write the training algorithm for log linear models, or the general model that I'll discuss later, you can try different batch sizes. It's a hyperpackage. Alright. Okay, now we've completely defined our log linear model. Okay, let's recap. The modeling target is the conditional probability of the output class given the input. Okay, py given x. Conditional probability. The parameterization is defined similar to last week. We define a feature vector over x and y. And our model parameters are a parameter vector as large as the feature vector. We assign a model parameter to weight each feature. Okay? And the model score is calculated as either the sigmoid of theta dot phi or the softmax of theta dot phi, depending on binary class multi-class classification. This is the parameterization step. The training step, the training objective, is the minimum of the negative log likelihood. In chapter 5, we will learn what it means. Why you say minimize negative log likelihood. Okay. And the training process is done using a numerical method called batch stochastic gradient descent. That's the whole model. Now you can build a model now yourself. During testing, given an input, you want to find an output class label. The process is the same as your perceptron and SVM. You don't really have to calculate the probability, but you just enumerate all possible class labels. You calculate the model score theta dot phi, and you select the one that has the highest score. Why does that work? Because your sigmoid softmax process are monotonic. So the higher your theta phi is, the higher the probability is, right? So essentially you choose the most probable output. When you really need a probability, you apply these functions. That's the testing scenario. Now that the model is so similar to the perceptron algorithm, okay, in testing and in parameterization, we want to compare the training process with the perceptron as well to understand why, the reason that we end up getting a probability score. So let's do a comparison. We take the binary case and multi-class case respectively. If you look at the binary case, right, the initialization could be all zeros. The iterative process could be completely similar. You all go through the training examples one by one, okay? And the update process is also very similar. You add feature vectors to model parameter vectors. What's the difference? The difference is that the perceptron makes a hard decision, okay? It uses the current model to predict the output class. If it's correct, we don't do any update. This, in machine learning, is called a passive update. Passive update. So you don't do update unless it's necessary. Okay. For perceptron, if your model makes an incorrect output, what does it do? It adds the positive feature vector to your parameter vector, right? Or it subtracts the negative feature vector from your model parameter. That's a one-off process. Okay, so hard decision. But for our log linear model on the left-hand side, you see two differences. First, no matter whether the output is positive or negative, right, no matter whether your output is correct or incorrect, you do the update. Okay, you do the update. What is the update? When you do the update, you have a weight to your feature vector. Okay? For positive classes, the weight is the negative model score. What does it mean? Think about it. If given a positive instance, right, your model believes that the probability of it being negative is 1. Your model is confident that it's 1. Right? It's a negative instance. Then you will do exactly the same as the perceptron update. You just add 1 times the feature vector to the model parameter. However, if this probability is less than 1, right, the model is not 100% confident that it's a negative instance, then what does it do? The more confident you are, the more aggressive I update your model, right? This is reasonable, right? The more incorrect you are, the more confident you are wrong, the more we update you. If you're completely confident that there's no chance for this instance being negative, then this number of 0, then we don't update the model parameter. It's again similar to the perceptron. So it follows the perceptron only if the model is completely confident. Otherwise, we will decide the strength of my model update according to the model probability. And by that reason, the model ends up giving a probability score that's the most reasonable. Okay? So we found great similarity between your logistic regression model and your perceptron model. How about the multi-class case? Let's look at the next slide. The two algorithms are very similar. Both of them uses the difference between the gold feature vector and the incorrect feature vector to update the model. But the perceptron algorithm is again very decisive. It only samples the highest scored negative output. Okay. You first find z, okay, which is equal to the class label that gives the highest model score. Okay? And then you update the model only using the gold output and this mostly incorrect output, conditioned on the fact that this incorrect instance is scored higher than your model score. Again, it's a passive update. If your model is correct, then we don't update. Otherwise, we adjust parameters. In contrast, on the red boxes shows your log linear model. It does the update, first of all, not only for one incorrect label, but for all possible class labels. Now for each class label, it makes adjustment according to how confident you are according to the model. If the model is very confident on one negative class label, then it will put a lot of weight on the update according to this feature. Okay? That explains why your model ends up with a probability score. Alright, so now we're done. We found a lot of similarity between log linear model and perceptron model, and we explained why it ends up with probabilities. The next thing we do is, last week we learned support vector machines. We only learned its training objective, but we did not discuss how it is trained. Now that we have a numerical optimization method, we can apply this optimization method to train SVMs, right? So, first of all, what is the training objective? Let's recap. The training objective is to maximize the score margin between positive and negative instances and the separating hyperplane. Right? So that's the support vector machine. And in order to integrate slack variables or violations, if your training instances are not completely linearly separable, then our training objective becomes like the next slide. So you minimize a half of theta squared. What is it? This is the distance between the support vectors and the hyperplane, right? Plus the sum of maximum 0 and 1 minus y times theta dot phi x. What is that? That is the slack variable. Due to time constraints, I didn't explain in detail to you, but I assume you read the textbook. So, if y times theta dot phi, okay, is greater than 1, it means that there's no violation. Positive class instances are way above the hyperplane, and negative ones are way below the hyperplane. That means y times theta dot phi is greater than 1. Okay? These don't violate the support vector assumption. So in those cases, we just put the result to 0 because we have maximum 0 and 1 minus this thing. No violation. If everything behaves, then we fall back to the standard SVM, right? So we minimize a half of theta squared. But if this thing, right, is less than 1, if it is less than 1 and greater than 0, what it means? It means that it's still correct, but it's not safe. It falls between the support vector and your hyperplane, okay? But if it's even greater than, if it's even smaller than 0, what it means? If it is even smaller than 0, it means that the model makes an incorrect prediction, right? It falls on the incorrect side of the hyperplane. Alright, so this means violation. We want to minimize these violations. We minimize the slack variables, okay? Now we got this training objective. We want to maximize, we want to minimize this using stochastic gradient descent. So what do? We take the derivative of this thing with respect to theta, right? And we plug the gradient into the SGD framework. We can train SVM. So, how do we take the derivative? Let's look at it. So a half of theta squared, easy. We can have a derivative. But there is a maximum function. A maximum function doesn't have a derivative. It doesn't have a well-defined derivative, right? Because there's a hinge point. At this hinge point, you don't know the derivative. So what do? We take subgradients. We break this maximum function into two halves. Right? If there's no violation, this number is equal to 0, then it's a flat line here. It's a flat line. The derivative is 0 here. If it is greater than 0, what do we have? Then we have the function as 1 minus y theta phi, right? So under that condition, it's a slope. Then we take the derivative on the slope. So when we break this function, then the gradients are defined in the last equation here. We first decide whether 1 minus y theta phi is less than 0. Okay? If it's less or equal to 0, we're fine, no gradient. So the total gradient is just lambda theta. By minimizing half theta squared. Otherwise, we have a violation, then we have another sort of gradient. It's lambda theta minus y times phi. This is easy. I don't have to even write on the blackboard. Okay. It's quite straightforward to take this gradient. Okay. And now what we have to do is we have to plug this into stochastic gradient descent, and we arrive at this pseudocode here. Okay, we just take a brief look at it. We go through the training instances multiple rounds. For each training instance, we decide whether y theta phi less than 1. If it's less than 1, we update it using one equation. If it's not, we update the model using another equation. Okay. Let's go to the multi-class classification case. Again, the features are not x only now, but it's x and y. And the objective function is a half of theta squared plus c times sum of max 0, 1 minus theta dot phi xy plus the maximum y, the highest scored y, theta dot phi xy. Okay. So what is the second half? The second half is again the score violation. We want the gold output to be scored at least 1 above the negative output, right? So if it is above 1 plus the negative instant score, then we're fine. We don't have a violation. So that's the max sign. But if it is smaller than that, we have a problem. We have to minimize this violation. So this is the second term. When you understand this part, the gradient is easy, right? Because the first term has a perfect gradient. The second term doesn't have a gradient. So we have to break this whole function into two halves. So one half doesn't have violation. We have gradient lambda theta. The other half has violation. We have gradient lambda theta minus the difference of the feature vectors. Wow. And we plug this into the SGD algorithm. We arrive something again very similar to the perceptron algorithm. What we have is we iterate through all the training examples from a random model, and we find the model output. Okay, and if the output doesn't satisfy a score margin, okay, then we perform a model update by adding the gold feature vector to the parameter vector and subtracting this incorrect model output feature vector from the parameter vector. Very, very similar to perceptron, reminiscent to what we learned last week. So let's do a formal comparison. So in both binary case and multi-class case. For the binary case, okay, both algorithms have a condition. The condition of the perceptron is whether theta dot phi is smaller than 0. But the condition of the SVM is whether y theta dot phi is smaller than 1. So which one is more strict? SVM, right? It asks the score to be greater than 1 or smaller than negative 1. It has a safety margin. Perceptron doesn't have it. So perceptron is, again, a passive algorithm, but SVM is more active. Okay? So the update now is almost the same. You just update the model parameter using y times 5. Okay? Similar here. But SVM has another term. It subtracts lambda theta from theta. It shrinks theta. What does that do? I'll talk about it later. Okay? So two differences, right? At least two differences. Two salient ones. One is that SVM is more conservative in the condition. The second one is SVM always shrinks theta. But otherwise they are the same. Perceptron. Now multi-class case. Again, both SVM and perceptron tries to calculate the model output. And then the update is the same. But there are only two differences. First, SVM is more conservative. Perceptron let the instance pass if the output is correct. But SVM doesn't let it go unless the goal score is higher than the incorrect score by a margin of 1, right? Secondly, SVM shrinks the model parameters. Okay. Alright. By comparing the two algorithms, we immediately know that the perceptron does have something to optimize. Last week, we didn't mention that the perceptron had an objective function, right? We said it's an online algorithm, but now all the discriminative models are online. So, perceptron's training objective function is here. If we just compare the gradient and reverse, like we reverse engineer this gradient, we find that perceptron actually optimizes this thing. It's a violation term with 0 rather than 1 without the half theta squared. That's the perceptron training objective. Okay? Alright. Why do I take the pain to do all this computation? Alright. Because we want to generalize all these discriminative models into a simple form. Now let's look at this comparison. We learned 3 discriminative models: perceptron, SVM, and log linear models. And we learned them for both binary classification and multi-class classification, right? And all of them had the parameterization of theta dot phi. Okay, we wrap that with a function f. We take this f as an activation function called activation function. For perceptron and SVM, this is the ID function, no activation. For log linear models, it's either sigmoid or softmax activation. Okay, so f of theta dot phi for all the models. For testing, they're all the same. You just enumerate all possible output, you calculate theta dot phi, you select the most high score. This is for testing. Of course, for training, they are all similar, but different. Okay. So let's first draw the parameterization into a simple model. We call it a generalized perceptron, or a single layer neural network. All these models are a building block of a neural model. Okay? They can be treated as neural networks. We will come back to that in chapter 13. But they are just one layer neural networks instead of multiple layers. We have a parameter, we have a feature vector, we have an activation function, and we have an output class. Okay? Take the binary case, it's just a class of 0 and 1 with the sigmoid activation functions. If you take the multi-class classification case, then there are multiple output neurons, right? The input is a vector, the output is also a vector. So every element in the vector has a score, normalized by softmax. So we have a one-layer neural network. And how do we train the neural network? Okay, the training is also unified. It's stochastic gradient descent. Okay, and we can write it in the pseudocode. Very simple. So we have an objective function which can be different. But when we train the model, we go through all the training instances multiple times, maybe in batches, and for every instance we calculate a gradient, and we take a learning rate, and we just update the model. Alright? But the parameter update function is different in the pseudocode. How are they different? Let's take the table. Let's take for binary classification, as we already summarized. Okay, you can also read the textbook offline. They are similar but different. This is for the binary case. Now for the multi-class case, let's look at the second slide. They are all similar, also similar, but have slight variations. Okay. As I mentioned to you earlier, these differences reflect differences in the training objective functions, right? So let's compare the training objective functions in one table for both binary and multi-class. Okay, these are the training objective functions. They all try to minimize something. For both perceptron and SVM, they minimize something related to the score margin. For log linear models, they try to minimize the negative likelihood, right? Different. Oh, come on. So why do we have different objective functions, although all of them try to make the model correct, perform correctly? Why do we have this? Well, this will reflect some principal differences. We can draw the loss functions for binary classification. Let's see the figure. Let's see the figure. In the figure, we draw the correlation between the model score and the loss. Okay, the model score and the loss. Let's first look at the dashed line. Dashed line, this zigzag line. What is it? This is a theoretical case. What do I mean? It's called 0-1 loss function. 0-1 loss. When your model score is above 0, okay, your model makes a correct prediction, right? So you don't have a loss. The loss is 0. But when your model score is less than 0, your model will make the incorrect prediction. You'll have a 1 loss. Okay? This 0-1 loss means whether your prediction is correct or not. Right? Correct or not. It's a theoretical loss. Why? Although elegant, it doesn't have a derivative. This loss function doesn't really, cannot be used to train a model. This is what we understand. Now the other three lines, the other three curves, are the SVM perceptron log linear models. As you see, they all decrease, right, as the model score increases. In other words, the higher the score we give to positive instances, the less the loss are. That makes sense, right? We want to give positive instances high scores. And they all increase as my model score goes more negative. That makes sense, right? We want to penalize negative scores for positive instances. But their shapes are different. For perceptron and SVM, the shapes are like hinge shapes. You have sharp turning location. Perceptron, the location is at 0. SVM, the position is at 1. As we know, it's because they have different, they're different in taking the margin. But they all grow linearly as the model score grows to the negative infinity. Log linear models instead don't have this hinge point. Okay? It's a smooth curve. Okay? It never goes to 0. It tends to 0 when the model score tends to infinity. Okay? And tends to negative infinity when the model score tends to negative infinity. So these are different shapes. So you can understand there are some philosophical differences in defining the losses. But I didn't explain why yet, right? I didn't explain why yet. Why? So let's look at the next slide. Overall, right? When we define a loss function, what do we want? What do we want? We want to minimize the expected risk. What do I mean by risk? The risk means that you define a loss when your model makes an incorrect prediction, right? You risk losing the accuracy, right? What do I mean by expected risk? The expected risk is when you're given any input x, right? What is the chance you have a loss? You make an incorrect prediction. Okay, this loss, as defined by SVM and perceptron, are these linear scores. Okay, the larger the loss. For SVM, for log linear models, it's a probability, log probability. So, what you really want to minimize is the expected risk at any training instance, so that you can do perfectly during test time. But unfortunately, you can't do that because you can't see every possible instance, right? What we have is only a small set of training data. These training examples are numbered capital N. So if you can't minimize the expected loss risk, you turn to minimize the empirical risk instead. Okay? What is the empirical risk? You can take the training set as a sample of your general set. Right? And you assume that every training instance has the probability of 1 over n. The empirical risk is then the average of the loss you define over the training set. You minimize this empirical risk to indirectly minimize the expected risk by assuming that your test data is distributed similarly to your training data, right? This is called empirical risk minimization. This is the principle of all the machine learning algorithms that we will see in this course. But now the research direction is still moving. So in addition to this empirical risk minimization principle, we should also consider causality, etc. Right? So that is beyond this course, and this is still an emerging direction of machine learning research. Okay. After all, most of the machine learning algorithms you see follow this principle. Right. So next, we discuss the difference between SVM and perceptron. Let's look at the equation. So SVM and perceptron, in addition to the differences in the margins, right? We also have this theta squared thing to minimize. What is it? What is it? It came from the margin we had, okay, between the support vectors. But in the end, you shrank theta. You shrank your model parameters, okay? By shrinking theta, you effectively shrink the weight on your features, right? Imagine your theta square is large. What does it mean? It means that you might have large weights that correspond to specific features, right? Because your theta, every element in your theta corresponds to every item in your phi, right? If one element in your theta is huge, then in the end, that phi will play an important role in your decision, right? That is risky. Why? Because you never know whether that phi is something peculiar to your training set. Because your training set is always a subsample of your general data, right? We discussed the generalization and fitting last week. You see, anything that fits your training data well doesn't necessarily generalize well. you have overfitting. So a huge element in theta will risk you overfit data. So reducing the squared norm of your theta reduces the chance of overfitting, and thus regularization will boost generalization in general. Okay? Right. So that sort of explains how do you soothe the difference between your empirical risk minimization and your expected risk minimization. You can bridge the two with regularization. Now, of course, in addition to L2 regularization, or minimizing the theta norm square, you can also do L1 regularization, which is to minimize theta itself. Okay? The norm of L1 norm of theta itself. Okay. Now, when you understand these two, okay, you can look at the perceptron SVM again. They're identical, right? The violation part of the two algorithms are almost identical. So they are called a margin-based loss. Okay. You can add regularization terms to perceptron as well. So SVM can be treated as a regularized perceptron. You can add regularization to your log linear models too, to your neural networks too. Okay. Okay. So now we know that we have a generalized perceptron neural network. We can define different training objective functions. We can define different regularization terms. We can define different iteration numbers, different features. They're all hyperparameters. So we can end up with a lot of models. I highly suggest that you try tuning these hyperparameters in your experiments. But when you have a lot of models, right, how do you know which is better? This is the next topic. Well, you said we have the test data, right? We just train model and tune the hyperparameters on the development set. And then we run different models on the test set. We compare the performance. But now I ask you, one model is 93% accurate. The other model is 92% accurate. Which one is better? You say, of course, the 93% one. But wait, these numbers are only on one set of test data, right? But different test data can have different distributions. How do you know 93 must be better than 92 on expected data, general data, rather than your particular test data? Alright, so this is again limited empirical observation here, unlimited possible test. Okay. Something that can be a tool to convince the person who asks this question is significance test. What is significance test? The principle is that you have an assumption that the two models are actually not so different. Okay, they are essentially not different. This one, in general, doesn't perform better than that one. Okay, it's only by chance that in the test set, this one is better than that one. Okay, so this equal performance assumption is called the null hypothesis. Okay, significance test is a means to estimate the probability of this null hypothesis. You have a lot of different statistical models to do significance testing. For example, students' t-test, etc. Okay, but in the end, you all get a probability of the null hypothesis. This is called the significance level. Of course, the smaller the better. Generally, if you get a significance level smaller than 0.05, you can be convincing. Okay, less than 5% chance. But if you get a significance level smaller than 0.01, you're more confident. Smaller than 0.001, even better. Okay? Okay, you understand the principle. I don't have time to explain algorithms to perform significance tests, but at least you should read about t-test. Last content of this week. Okay, again, you have a lot of models, right? You train a lot of models. Some perform better, some perform not so accurately. But these are only on one test set. You don't know, okay, in the wild, how to make use of these models to achieve even safer classification. It's like we have 10 of us, okay? Each of us can make a decision. Someone's decision more reliable, someone's decision less reliable. But when we come together, there must be a way for the 10 of us to make a safer decision. So this is called ensemble models. It's a common technique in NLP to achieve better results. For ensemble modeling, I introduce 2 or 3 techniques. So one is called voting. The principle of voting is simple. You have 10 of us. Let each of us make a decision. And then you count the number of decisions on each class label. And according to it, you can choose majority vote and other strategies. This is like, you just take the standard voting strategy. We can also have weighted voting. Say, if you trust someone more than others, you assign more weight to his vote or her vote. Right. When your model scores are in the same scale, for example, they are all conditional probability, you can also take the model confidence into your vote. I am 0.9% confident that this is this class. Then you weigh my 0.9 rather than weigh my final answer 1. So these are weighting strategies. Another way to ensemble different models are called stacking. Say you have 10 students, okay, and you have a teacher. Now each student, okay, can give us a decision. You say it's 1, you say it's 2, you say it's 3. Now the teacher will, okay, look at all the student decisions and then make my decision. So this is called stacking. You have a layered structure. So the lower models make decisions and the higher model use the lower model decisions as features, okay, to make the higher model decision. So it's a layered structure. Okay, you enlarge your higher level model feature vector, okay, by adding a lot of new slots. These slots are lower level model decisions, and you train your higher level model by consulting the lower model decision as features. However, there's a risk, okay? If your lower model and higher models are all trained on the training data, then you have a problem. What is it? You can imagine. Because your model is always expected to perform better on your training data, right? So the lower models will give you more reliable features in training compared to doing testing. Let me take another analogy. So suppose we take the same test. I consult my teaching assistant. Okay, every time I answer my questions, I look at my teaching assistant's answer before I answer. But during training, his answers are mostly correct, right? Because he's trained on those answers. I'm very confident. I look at his answer and I answer correct. During testing, disaster happens because he never sees the test questions. During training, his performance is 99%. During testing, it's 73%. I learned to rely on his answers during training. And during testing, I still look at his answers in the same way as before. So I performed very badly, okay, during testing. How do we solve the problem? There's a trick called k-fold jackknifing. Okay, we try to simulate the test scenarios during training by cutting the training data into k spots, right? K slots. And we train my teaching assistant using the other k-1, okay, before letting my teaching assistant to predict the other fold. And we do this in a rotating manner so that every training instance is predicted as a test instance. And then I can train myself using the predictions, and I can perform better during testing. This is called k-fold jackknifing. The last topic is called co-training. It's another way to ensemble different models, but this time using a lot of raw data, unlabeled data. So the basic idea is still like we vote, but we don't vote on the test directly, but we vote on training data. So suppose we have a lot of exam papers that were never answered. What do? Each of us answer those exam papers, okay? And we compare our answers. Are we confident? Are you confident? If we're both confident and we're the same, okay, then fine. This is the gold answer. We treat that as a gold answer. And we retrain ourselves using this self-exercise. This is called co-training. Interestingly, even if you just do self-training, you can improve your performance. Just yourself doing simple question answering, and you train yourself again. I don't have to explain them in more detail, but you can read your textbook yourself. I explained the idea. Okay, that's all. So in the first 4 weeks, okay, or 3 technical weeks, what did we learn? We learned 2 types of classification models, right? So one is generative models, one is discriminative models. And all the discriminative models is just a single layer perceptron, all right? We come back to perceptrons in week 13 when we stack them together. But before we move to week 13, we still have something more to learn, okay? More theoretical part to learn. So next week, we'll come into information theory and explain why do you have maximum likelihood estimation. Right? We'll look at entropy, perplexity, K-out divergence, and other things in NLP. Okay, see you next week.